Alright, so this video is going to be about elimination reactions. And so we've seen the general mechanism for it already, but let me go ahead and give that to you again. So we've got basically an alkyl halide, or something with a good leaving group on there. I'm going to highlight this hydrogen in blue because that's of interest, as well as this X that can represent the halogen or just a leaving group in general. Okay, so this particular carbon is called the beta carbon, while the one with the actual halogen on it is the alpha carbon. Okay, so alpha beta, right? And since that beta carbon is identified as a beta carbon, anything attached to it, like this hydrogen, would be a beta hydrogen. Okay. Now this is important because for an elimination reaction, we essentially have to remove a beta hydrogen, and then those electrons create that pi bond, which kick out that leaving group, and therefore forming an alkene. Plus we have our anion as well as our conjugate acid for whatever base we used. Alright, so this type of reaction has a couple names, and one is kind of, I guess it's specific, is beta elimination. Okay, so that's because we are eliminating two things that are beta to one another. And then it's also more specifically called dehydrohalogenation, because we're removing a hydrogen as well as a halogen. Okay, so dehydrohalogenation leads to that alkene and is an elimination reaction. So when it comes to the base, which bases are ideal? So we want non-nucleophilic bases because, as you can see, there's a halogen on there, and we can do substitution reactions with nucleophilic bases, right? Remember, bases and nucleophiles are very similar. So some common bases that we can use are hydroxide and alkoxide. That's what that OR minus is. Of course, those are nucleophilic as well. So that tert butoxide is a great choice for non-nucleophilic strong bases. Now I want to abbreviate or kind of lay out what that R is. It could be an OCH3 or OCH2CH3, so etc. Any alkyl group. Okay, and then that OTBU, that's the chicken foot. So that's tert butoxide. So of course, any negatively charged thing has to have a counter cation, and so those might be seen either directly next to those bases or not. But sodium, potassium, lithium, etc., any of those alkali or alkaline earth metals. So now let's try a couple examples. So I'm going to walk you through it basically how I would do it. Definitely doesn't need to be done this way, but I find it to be an easy step-by-step process. So first of all, what you want to do is, if you weren't told that it's an elimination reaction, you want to identify that it's an elimination reaction somehow, which we'll get into later. But for now, hey, this is an elimination reaction, and we got some bases here. So those bases want to remove a proton. More specifically, they want to remove a beta proton. Okay, so we've identified our alpha carbon here with the chlorine on it, and then this is a beta carbon right here on the right side, and then we've also got a beta carbon on the left side. Okay, and the thing about this one, I like this problem because the beta carbon on the left side does have a beta hydrogen, but the one on the right does not, and you need to be very aware of this when you're drawing your products. So base comes in, removes that beta hydrogen, creates that pi bond, and kicks out that leaving group as a chloride. So we end up with an alkene, right? Or that's that one, right? Sorry. Or we can get this alkene. So notice they are different stereoisomers as well as diastereomers, because they're non-superimposable mirror images. But we'll get into the stereochemistry of these things later. So alpha carbon identified. This one's fun because we've got 3 beta carbons and also 3 beta hydrogens. Okay, so how many different products do you think we're going to get? Well, we can draw Each of those, right? I'm going to swoop on each of these protons with the tert butoxide, which then creates that alkene product. So let's go ahead and remove those black marks, and then I'm going to use different colored arrows for the following products. So swoop on this beta hydrogen, and we've got, let's see, this. Try and draw the product out yourself if you can, but there's this alkene, right? And then let's do a different color. We'll do red. Grab that one on the top. Bada bing, bada boom, and we can form this alkene. Okay. Now I know some of your favorite colors are the poopy brown arrow, so I'm gonna go with that poopy brown arrow and get this product, right? So obviously, at least, so the one on the top, I kind of highlighted that red and blue pi bonds. Those are the same. If you think about them just rotating, kind of flipping them like a pancake, they are the same compound, okay? However, the bottom alkene is clearly different and is a constitutional isomer, okay? So this is definitely possible when you have more than one beta hydrogen. And obviously, I mentioned it before, we'll get into the stereochemistry later. Right now we're just doing basics. All right, so let's take a look at some alkenes. I guess more specifically, like the types of alkenes that we'll see. So meaning the substitution patterns, okay? So first, let's talk about the most basic alkene. Well, basic has a whole new meaning in chemistry, so it's most simple alkene. Basic isn't just your pumpkin spice lattes, is it? Which I love. I'm definitely quote unquote basic in that sense. We got a sp2 hybridized carbon, two of them obviously because we got the most basic alkene. 120 degree angles. And then what we want to do is kind of draw out these pi bonds, okay? So bear with me, okay? So I'm not technically an artist, so I'll draw these pi bonds. The p orbital is pointed upward, or in a vertical axis, and then we've got those obviously overlapping to create that pi bond, right? And so that's really what it's all about when you're forming alkenes. Ethylene or ethene is the name of this most simple alkene, and so this, we can move forward from this and start putting R groups on that one of those carbons, right? And so this is what we mean by types of alkenes. Okay, so we'll have one R group, then two R groups, then three R groups, and then what you think? Of course, we're gonna finish it off with 4 R groups. Okay, and remember, R groups are just like carbon chains. Okay, so it could be small, it could be big. This, since it has 1 on there, is a mono-substituted alkene. This one right here, since it's got 2, is di-substituted, and then you guessed it, we go to tri-substituted, and then, 4 is tetra-substituted. Okay. All right, so let's draw a molecule out and see if you can identify if it's mono, di, tri, or tetra-substituted. So, boom, 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 boom. We're gonna draw vitamin A here. And we've got lots of alkenes, or double bonds, in vitamin A. That's why it's a fat-soluble vitamin. So on this one we've got, starting from the left, we've got 4 things coming off of that those carbons. So that's tetra-substituted, okay? Sorry, let me delete those circles real quick, and I'll write tetra out for you. And then basically that's what we want to do across this whole thing. So we got 1 carbon here, 1 carbon here coming off that alkene. So therefore that is a di-substituted alkene. Now we got 1, 2, 3 carbons coming off of this alkene. So that's tri. And for this next one, we've got 1, 2 carbons coming off that alkene, and it's di. And then for the next one, we got 1, 2, 3. So that's another tri. Okay. And that's pretty much all you got to do to identify if it's mono, di, tri, or tetra substituted. Just pay close attention and then you'll be fine. But why is this important? We'll see in a little bit. But I want to introduce to you another form of an alkene, I guess. So we do know of these already. So we have the cis isomer as well as the trans isomer, right? And so these are important as well because these cis isomers are, well, they're going to have different stability, and we'll see that in a bit. But that's because we have two groups on the same side, right? For the cis, and then the trans, they're completely opposite from one another. So if you think about it in terms of steric hindrance, they are farther apart. Okay, so since we're on the topic of stability, let's go ahead and draw this arrow from left to right, going from mono to tetra substituted, because that is the direction of increasing stability for alkenes. Because as we increase the number of R groups, we're going to have an increase in stability. Okay. Now, on that same note, trans isomer is more stable as well because they're more stable than the cis because of sterics, right? So if we look, like I mentioned before, the trans has the groups polar opposite of one another, while the cis, this is my attempt at drawing like an electron cloud for that group. They're kind of bumping up on one another, and so there's steric hindrance there, and they need some room, but they can't because those angles are locked in at 120 degrees, and we're stuck. Sorry about it. Now, one explanation for the stability increasing as you increase the number of R groups is that R groups donate electron density, and the sp2 carbons in that pi bond are more willing to accept it. So that increases the stability, right? But I want to give you a little bit more details on why the more substituted alkene is more stable, okay? So I'm going to call this stability 2.0. You might want to write this down. Pay attention. So let's say we've got this here alkene right here. This is an explanation for like cis and trans. Okay, so imagine we had an acid catalyst in here, and we're actually able to swap back and forth in equilibrium to from a trans to a cis alkene. Okay, so you don't need to know why, but what you do need to know is that the population of the trans is 76%, and the population of the cis is 24%. Now, this can be done spectroscopically to determine if it's cis or trans, right? Because you have different coupling constants for those hydrogens. But remember, delta G is equal to minus 2.303 RT, the gas constant times the temperature, and then log of KEQ, which is obviously the equilibrium constant. And we're talking about equilibrium populations of products, right? And so this gives us that actually depends on the energy difference between the two products, right? Or the reactants and the products in this case. And remember that delta G is basically it's the free energy, and free energy delta G was approximately equal to delta H, which is enthalpy, and so this is basically telling us that the relative energies of the trans and the cis are related to delta G, or are directly related to delta G, which is related to KEQ, and so that's why the stability of trans being lower results in a higher population of trans in the equilibrium of this particular like acid catalyzed reaction. And so again, just showing you the relationship between stability as well as equilibrium. Okay, so that's proof that the trans is more stable, but we can also do it with this particular reaction below. We have an alkene. If we throw H2 gas on a palladium catalyst with this, we will end up with a hydrogenation product. Again, don't worry about what this reaction means or how we got it or whatever. Just know that we're basically adding hydrogens to those two carbons within the alkene bond. And so if we go from the left side to the middle, we're going from a trans to the alkane, which is butane. And then as we go from the right to the center, we're going from a cis alkene to the butane. So we got trans to butene, we got butane, and then we got cis to butene. So notice that they are both going to the same product, so it's the same end point, okay? Same energy as well. And so hopefully you remember them, but you can do like heats of hydrogenation, for example. So we can find out how much energy is released or put into the system of a reaction. And in this case, the cis isomer, the heat of hydrogenation for this is minus 120 kilojoules per mole. So remember, that means we're releasing energy, right? Because it's negative. And for the trans isomer, we have a heat of hydrogenation of minus 116 kilojoules per mole. Okay, so since that energy value is lower, that means that the trans isomer was stable in the beginning. So let me show you using a graph. We got red and blue circled here, okay? So the red curve is going to represent the trans isomer. The blue curve is going to represent the cis isomer. So let me draw you my lovely reaction coordinate graph here for you. So remember that the product in the end is butane, right? So that product is going to be the same. Okay. So now what we want to do is, we know that the cis isomer and the trans isomer are different in energy, right? So let's just go ahead and draw two arbitrary lines here. We don't need to indicate which one is which, but this is what the curve would look like. Okay. Since the transition state looks more like the reactants, it's going to be lower. So that means we're going to have the curves kind of being set up like this. Now let's take a look at the enthalpy for these given reactions. So remember, that's basically enthalpy for the entire reaction. The small arrow and the big arrow, the big arrow represents the larger energy difference, right? And so that means that's going to represent the minus 120 kilojoules per mole. So that's the higher energy starting material, and that led to a greater loss of energy in the end. So that's the cis isomer. And now this small curve right here in red is the trans isomer, because it's lower energy, and that resulted in less energy being released. And again, another reason, or another, I guess this is more proof that the trans isomer is more stable, and in this case by 4 kilojoules per mole. Okay, and so I'm just drawing out all on the y-axis. You got 120 on the and 116, just so you get an idea as to what I'm really trying to say about the energy difference and the loss of energy, and how we can relate the heats of hydrogenation to the stability. Okay, so it's all about sterics when we're talking about trans. Okay, because other than that, there's no difference. They're the same bond connectivity. Okay, what we can have, and what we kind of explained before is, very briefly, is that we have an sp2 versus sp3. Okay, so the electron acceptor would be considered sp2, while sp3 is electron donor. Okay, and we can justify this by basically the more s character is closer to the nucleus, so it's the electrons are more stable there. So it's like, hey, throw them in here. All right, here's an alkene with the p orbitals pointed up, right? We got them on the vertical axis. That overlap is creating that pi bond in red. Now I've drawn this hydrogen explicitly because we don't care about the other ones, at least for this drawing, right? So remember, in the carbocations we had overlap of this sigma bond with the p orbital, right? And so this is actually going to happen here as well, and so that creates more stability. So the more R groups that you have, the more of this hyperconjugation or overlap between these sigma bonds and that p orbital, and so it's going to create more stability. I like to think of it as almost like a pseudo resonance, right? Like almost like it's an extra bond in there, and so it's holding everything in tighter, and it's stronger, and it's just, that's the stability. I mean, it is what it is, right? So in a very superficial manner, that's our explanation. Okay, so let's go ahead and draw out just 3 different isomers of an alkene. So we've got 4 carbons and 1 pi bond, right? So the ones on the right are cis and trans isomers, and this one's disubstituted, so is this one, right? But the one on the left is monosubstituted and it's just a different alkene in general, right? So constitutional isomer. The one thing I want to point out is the number of sp2 sp3 bonds. Okay, so I mean the CsP2 to CsP3 bonds, and that's going to help. If we the more bonds that we have, the more stable that alkene is going to be. And so this sp2 sp3 bond on the monosubstituted, there's one of them there. And if we look at this disubstituted cis alkene, we have 2 of them here. Okay, and so this right here, the CsP2 to CsP3 bond is stronger than a sp3 to sp3 bond. And so since this cis disubstituted alkene has more of those, then that is more stable. Okay, and so that's kind of like another way to explain the stability of a more substituted alkene, because as a result, you're going to get more, if you have more substitution on that alkene, you're going to get more CsP2 to CsP3 bonds, and so it's overall just stronger. Now, of course, that stability of these 3 goes from, it increases in stability as you go from left to right, and that's because the trans is more stable because of sterics. And so that's pretty much it for this one, and let me know if you have any questions. Okay, I'm sure you will.